Okay, let's dive right into this explainer and master the core logic of decision-making in C programming. As developers, the programs we write need to be smart. They've got to react to user input, adapt to different data, and make choices on the fly. So today, we're decoding exactly how to give your C programs a brain. Here's our roadmap for today. We'll be covering Intro to Conditional Statements, the if and if-else structures, else-if and nested ifs, logical and conditional operators, the switch case structure, and finally, a recap and programming patterns. Starting with Section 1, Intro to Conditional Statements. So, before we can write complex algorithms, we need to understand the fundamental language of the computer's decision-making process. The crucial point here is that a computer only really understands true or false. Conditional statements are basically how we translate our complex human decisions into that binary reality. It looks at a specific Boolean expression, like checking if a user's password is correct or if their bank balance is greater than a purchase amount. If it evaluates to true, the program takes one action. If false, it does something else. It's the absolute bedrock of software logic. Moving to Section 2, the if and if-else structures. Let's look at our first escalation of choice. The simple if structure. This brilliantly illustrates a one-way selection. Notice on the flowchart how the code only executes if the condition is true. Otherwise, it just bypasses it entirely. Looking at the syntax, you type the word if, followed by your condition in parentheses. If that expression is true, the code inside those curly braces runs. If it's false, the compiler completely ignores the block and moves on to whatever comes next. It's just a simple single detour on a straight road. To build those conditions, we use relational operators, which let us compare values. We've got standard math symbols like less than and greater than. But listen up. Here is a massive exam tip for you. Always, always remember the difference between the assignment operator, which is a single equal sign, and the equality operator, shown here, which is a double equal sign. If you want to check if x is exactly equal to y, you absolutely must use the double equals. Using a single equals in an if statement is honestly one of the most common syntax bugs in C programming. So, if a simple if is a one-way street, what happens when we want to pose an interactive challenge, like checking if someone is old enough to vote? We don't just want to do nothing if they're underage, we want to actively tell them they can't vote. To solve that, we bring in the optional else block. This gives our compiler a specific set of fallback instructions if that first condition turns out false. Look at the flowchart. We now have a distinct fork in the road. The true path goes one way, and the false path goes another. They never execute at the same time. You either run the F body or you run the else body. Now, what's really interesting here is how cleanly this syntax maps right to our voting problem. We test if age is greater than or equal to 18. If a user inputs 20, the condition is true, and it prints, you are eligible for voting. The else block is completely ignored. But if they type 16, the if condition is false, so the compiler immediately jumps down to the else block and prints, you're not eligible for voting. It's elegant and highly predictable. Section 3, else if and nested ifs. Real-world problems rarely have just two outcomes, right? What if a student's grade could be a first division, second division, third, or fail? We need more paths. By chaining else-if clauses together, we can check multiple conditions in sequence. But remember this, once a single condition is met as true, control stops and ignores the rest. This is vital for efficiency. If we check if a student got above 60% and it's true, they get a first division. The compiler doesn't even bother checking the 50% or 40% brackets. It just executes that specific block and then jumps completely out of the whole chain. For layered complexity, we can nest an if statement directly inside the body of another one. That means the second check only happens if the first check is already true. Think of it kind of like a security checkpoint. You check their ID first. If the ID is valid, you let them into the lobby. Once in the lobby, there's a second if statement checking their ticket to see if they can actually enter the theater. Let's trace the path on this code here. Our compiler first confirms the outer condition where I is less than 15, and only then does it step inside to evaluate the nested condition. So our variable I is 10. The first check asks, is 10 less than 15? Yes. We step inside the block. Then we hit the nested check. Is 10 less than 12? Yes. So we print that it is smaller than 12 too. Now, if our variable was 13, it would pass that first check, but fail the second, dropping right into the inner else block. Section 4, Logical and Conditional Operators. Sometimes writing out massive nested loops is just really inefficient. That's exactly where logical operators come to the rescue. These three operators, and, or, and not, allow us to elegantly combine multiple conditions into a single if statement. The double ampersand is and. the double vertical pipe is or, and the exclamation mark is not. Instead of putting an if inside an if, we can just say, hey, if condition A is true and condition B is true. Look at how the double ampersand and operator strictly demands both sides to be true, whereas the double pipe or operator is perfectly satisfied if just one side is correct. In this snippet, we test if A is greater than B and if C is equal to D. Because C is 10 and D is 20, they aren't equal. Since it's an and statement, the whole expression fails, and the console proves it by printing and condition not satisfied. But in the very next block using the OR operator, because A actually is greater than B, the entire OR statement passes, totally regardless of the second half. Now, for an ultra-concise alternative, C offers the ternary operator. This condenses an entire if-else block into a single line of logic, using just a question mark and a colon. It's called ternary because it takes 3 operands. First, you state your condition, followed by a question mark. Then, you put the value or action if it's true, a colon, and the value if it's false. It is fantastic for quick assignments, like finding the maximum between 3 numbers without having to write 10 lines of if-else brackets. Section 5, the switch case structure, our final escalation. When you have a variable that can equal many distinct, exact values, chained else-ifs get incredibly tedious. A switch statement tests a single variable against multiple exact matching cases, dropping the compiler right into the associated block once a match is found. You give the switch an expression, usually an integer or a character, and it jumps straight down the list looking for a case that perfectly matches that value. There are some rigid rules here, though. Each case label ends with a colon, not a semicolon. And please, here's a massive common mistake call out for your code. If you forget to type the break keyword, your program will accidentally execute all the cases below your match. We call this fall through. Once a switch finds a match, it executes everything below it until it hits a break command, which tells it to finally exit the switch block. Also, the default case at the bottom acts just like an else. It catches anything that didn't match. So why do we use this instead of chained else-if blocks? Simply put, switch cases save developers from extreme confusion by drastically improving code readability. If you're building a menu system where the user presses 1 to play, 2 for settings, and 3 to quit, an if-else chain just looks cluttered. A switch block makes it instantly obvious to anyone reading your code what each number does. This interactive task brilliantly illustrates the power of switch. Notice how cases 1, 3, 5, 7, 8, 10, and 12 are all stacked together to elegantly share the exact same 31 days output block. Because we intentionally didn't put a break after case 1, 3, or 5, the compiler falls through all those labels until it hits the print statement for 31 days and the final break. This means whether the user inputs month 1 for January or 7 for July, they land right in the exact same output. Doing this with an if-else would require a ridiculously long string of OR operators. Wrapping up with Section 6, Recap and Programming Patterns. We've covered a lot of ground today, from simple one-way streets to complex switchboards. Here is your cheat sheet. If-else is for binary paths. Else-if handles continuous conditions. Switch is your optimized multipath routing. Use and OR to combine logic. And always include break in your cases. Master these patterns, understand exactly how your compiler routes decisions, and you'll be writing flawless C logic in no time. So, with these tools ready to go, what complex problem will you solve next?